Okay, notes 2.4, differentiability and continuity. So we're first going to talk about differentiability at a point. So it says a function y is equal to f of x is differentiable at x equals c if and only if the limit of the derivative exists. That's the main idea, because notice how it's saying the limit as x approaches c from the left and the limit as x approaches c from the right are both equal to one value L. So we know it's differentiable if the limit of the derivative exists. There are some instances where the derivative may fail to exist, and that is at a corner, a cusp, a vertical tangent line, or a discontinuity. And that could be a hole, a jump, or a vertical asymptote. Okay? And then below I drew diagrams of what it means by corner, cusp, and vertical tangent line. Okay. In this example, it gives us the function the cube root of x, and it wants us to use the alternative form of the derivative. So notice it's giving us this definition, f of x minus f of c over x minus c, which again is just the alternative definition of a derivative. And it wants us to show that the function has a vertical tangent line at x equals 0. So for these ones, we would plug in the function, so cube root of x, and then plug in 0 for f of c. So since our function is the cube root of x, the cube root of 0 would just be 0. And then once we get here, we can simplify using our properties of exponents. And what we did is we end up moving this cube root down and then combining the exponents. And when we plug in 0 as x approaches 0, we get 1 over 0, which is undefined. And remember, a vertical tangent line, as we see off over here, is indicating a vertical slope, and we know the slope of a line, of a vertical line, is going to be undefined. Okay, so we have some more examples here. Okay, the next concept is that differentiability implies continuity. So if f is differentiable, then f is also continuous. So right here, differentiability implies continuity. However, the reverse is not necessarily true. Continuity does not imply differentiability because of these instances, so sharp corner, cusp, vertical tangent line, or discontinuity. Okay, so looking at this example off to the side, notice how we have this graph here. And at these points that are circled, notice that there is a cusp. So even though this is a continuous function, meaning I can trace this with my pen without lifting it up, at these instances where there's a cusp, so negative square root of 5 and positive square root of 5, I know that it will not be differentiable at those exact points. Okay, let's see. Okay, example 6 says find the values of the constant a where the function is continuous over all real numbers. So remember, in order to prove that it's continuous, these things need to exist. So f of c is defined, the limit of f of x as x approaches c exists, and also that the limit is equal to f of c. So in order to prove this, we are going to plug in 3 in for x, and then we're going to set these equal to each other. So when we do that, we are left with 9a minus 3 for this top one, and then 2a. So if in order for it to exist, they have to be equal to each other. So when we set it equal to each other, we're able to find the a value, so in this case, 3/7. Okay. So once we find this a value of 3/7, we can plug that in for that first equation up here, and plug in x to find what the value would be, which is 6/7. So this says when a is equal to 3/7, f of x is continuous at x equals c because the limit as x approaches 3 of f of x is equal to 6/7, which is equal to f of 3. So we're just proving this definition of continuity. Okay, we have another example here where we are checking if this is differentiable or not differentiable. So notice in our first step, we have to check if it's continuous. We prove that it's continuous. In order to move on to differentiable, the continuous one has to be true. Okay, so when we're checking if it's differentiable, we're now looking at either the derivative of these two functions, or notice here they use the alternative definition of a derivative over here. So what we find out is that since the limit of the derivative is not equal to each other on both sides, we say that g of x is not differentiable even though it's continuous. Okay, we showed that we could use a calculator to find the derivative. Remember, all you do on Desmos is type in the function, and then on the next line you would type in f prime of whatever number it was asking you. It's not like the calculator where you have all these individual steps. This is done very simply on Desmos. Okay, these are kind of just some review definitions that we just talked about in these notes. So if you want to pause here, make sure you have everything memorized. That would be a good point to end notes for.